Swayam Prabha. Digital India. Educated India.
Yeah, quickly figure this out. So, this is nothing but expectation of e to the power of t xi. Xi is 0 or 1. So, what I get is pi into e to the power of t plus 1 minus pi. Agreed? So, you are okay with this expression? Now, do a little bit of algebra, simplification. So, get 1 out, 1 plus pi into e to the power of t minus 1. This I can write as e to the power of pi into e to the power of t minus 1. Why? Because for any y, you can write this, right? Because if you expand e to the power of y, you get 1 plus y square by 2 factorial, so on and so forth. So, I am just neglecting the higher terms. So, this is the moment generating function of each xi. I now know that x is summation of xi. So, quickly figure out what is moment generating function of xt. So, apply that earlier theorem which divides the sum to products. I have already deduced each one of them. So, product of this is e to the power of e to the power of pi e to the power of t minus 1. Done? So, this exp means actually this e to the power of summation pi already we know to be equals to mu. So, I have been able to figure out the moment generating function of the sum of the Poisson trials. Right. Now, coming to the final theorem. Oh, sorry, I think there will be a minus here. Okay, let's now try to prove them. Now, remember, Chernoff bound is nothing but Markov's applied to this. My capital X is now the sum of 0, 1 independent Poisson trials. I know its moment generating function. I have to now suitably choose a t. That is what remains. So, I do one for you, and by the way, I mean Chernoff bound actually comes in very many different variants. It is like here I am just saying that x is greater than or equal to 1 plus delta mu. You can make statements like x minus ex mod is greater than something. So, you can make many kinds of statements, right. So, you have suitably different Chernoff bounds for each one of them. So, we will put some of them up on the tutorial sheet. So, what I do is I prove this one for you and leave the rest for you to do, because if you get the essence of one, the rest are just doing the calculus in a little bit different way, otherwise the philosophy remains the same. Okay. So, this theory actually tells you that if need be for your own particular case, you can derive your own Chernoff bounds that fit your particular application, and people do it. Maybe it's like right. This is what Markov is for you. Okay. Now, I have already deduced this one. This is already done. Right. E to the power of t minus 1 mu. Replace that. Now, choose your t suitably. Now, for any delta greater than 0, you see a good choice of t is a logarithmic function. because e to the power of log n is right. That is the reason. And this is obviously greater than 0. So, this is what I set out to prove. What did I need? Moment generating functions, the fact that if I am dealing with sum of independent random variables, the moment generating function of the sum is equivalent to the product of the individual moment generating functions. That allowed me to figure out the moment generating function of x, which was the sum of 0 1 independent random Poisson trials, and then it is just choosing a t, particular t. Now, for some cases, like in here it is like what I set out to prove allowed me to set t to be some log 1 plus delta, and things were nicely fitting in. There would be cases where you have to do calculus, because there was that minimization expression, right. So, that means you have to do a derivative in terms of t in some cases. So, that depends on the form of the Chernoff bound. So, I will put up some more forms for which just setting a t to log of 1 plus delta might not help. You might have to do a little bit of more calculus. Okay. So, there are two forms, remember, two forms. I have proved the first one for you, second one I leave as an exercise, and I will give you some more forms of Chernoff bounds, which again can be proved similarly. Same setting, meaning n 0 1 independent Poisson trials. Prove that for 0 delta less than equals to 1, probability x greater than equals to. So, you are varying delta in particular ranges. উদ্দালক এগুলোকে একটু এক্সারসাইজে ঢুকুন। So, as I told you, Chernoff bounds or Hoeffding bounds, they come in different formats, and which one you choose actually depends on the application that you are handling. So, whenever like we researchers have to use Chernoff bounds, we have to from a big repertoire of Chernoff bounds, we have to suitably choose which one to use, and that would obviously depend on the application in hand. So, these are kind of very popular ones. So, that is the reason I did this. Okay. So, we will do a corollary of this theorem, and then again go back to the same example we did in the morning. So, this corollary also has the same setting. Now, this corollary will actually follow the corollary that I wrote. So, it is x minus mu mod greater than equal to mu delta, right. This would actually follow from this 1 and 2. Why? It is easy to see that for the first term you can rewrite it as x greater than equal to mu plus mu delta, right. X greater than equal to mu plus mu delta, bring mu to the other side. So, you have x minus mu greater than equal to mu delta. Similarly, for the lower end, lower one, number 2, you will have x less than equals to mu minus mu delta, bring mu to the other side, x minus mu is less than equals to minus mu delta, fine. Now, if you now look into both of them and you can bring them together with the use of a mod sign, right, and then the mass on this right hand side gets added up, fine. So, what you are doing is, earlier your x was following only one, now you make your x follow both of them. So, now the range increases, right. So, you are also adding up the right hand side, that actually makes it 2 in here, fine. Again, this is an exercise which you should try. Fine. So, this is like now in a nice form that we know that for a random variable x, how far it is distributed away from its expectation by a certain quantity, and I have this probability value. Now look at, if you look into the probability value, it is e to the power of minus something. So, that is appreciably a low value, right. So, it is a negative exponential. Let us now apply it to our morning example. Remember the morning example? Let us get back. So, from Markov what we got, that x greater than equals to 3n by 4 had a probability of 2/3. There was appreciable improvement in Chernoff, it was almost a 1 by n inverse polynomial. Let us see what Chernoff gives us. Again, this capital X, what was it? N independent tosses of a unbiased coin, right. So, this is a setting of Poisson, right. Each one has a probability of now half. It is more than Poisson, it is binomial, it is actually Bernoulli trials, because each probability is same. So, the number of heads you can look at as sum of xi's. So, this setting of n coin tosses of an unbiased coin, and where each toss is the outcome of each toss is independent of all the previous tosses, is also a setting of sum of Poisson trials. All of you agree to that? So, that means it is also a fit case for application of Chernoff bound. Now, remember this, Markov you can apply almost anywhere. If you can just figure out the first moment, the expectation, Markov gives you certain result. Chebyshev is a little more difficult to apply because you need the variance. Chernoff is even more difficult to apply. Why? Because this complex event, which is modeled by the random variable capital X, you have to write it down as a sum of 0, 1 independent random variables. That is not always very easy. But if you can, then that is a fit case for Chernoff. So, in here it is a fit case for Chernoff. So, let us apply Chernoff and see if you can even get more than 4 by n. Okay, as I told you, which form of Chernoff would I use actually depends on the judicious choice of the designer. So, I will choose this one. X minus mu, right? So, mu for our case is, hey, mu for our case is n by 2. What is mu? Udalog, you have confused them with that probabilistic method. X is sum of xi's. This is half. So, expectation of xi is half. So, expectation of x is okay. So, x minus n by 2. So, remember that deduction in Chebyshev. So, how I brought down this x greater than equal to 3n by 4 to this format, right? Same thing. Now, just figure out what is your delta. Your mu delta is equals to n by 4, your mu is n by 2, that means your delta is half, and that means your delta square is 1 by 4. So, this is 2 to the power of 2 into e to the power of minus 1/3 this term, mu is n by 2 and delta square is 1 by 4. So, this gives you an expression like 2 into e to the power of minus n by 24. So, you understand the sharp fall. Markov gave you 2/3, Chebyshev gave you 4 by n, 1 by a polynomial, and this is giving you a 1 by an exponential, right? You all already know that an exponential grows faster than a polynomial. So, constant, constant, polynomial is a greater function than that, exponential is a greater function than that, but I am looking at 1 by each one of them, right. So, 1 by an exponential is less than a 1 by a polynomial. So, Chernoff is obviously giving me a much better bound, it is giving me inverse exponential. Okay. Now, as I told you at the very beginning that you can play around those things, right. This quantity that you want to say and the values. Let us look at one such example and try to understand its meaning and then end. Delta square, right. So, 6 log n by n, this is equals to 2 by n. Now, see, why did I choose such an expression? So, what I wanted to show to you was, mind you, Chebyshev gave you a bound like 4 by n, remember? Chebyshev gave you a bound of 4 by n, where, just look into the Chebyshev setting. So, I have given you a bound where Chernoff is giving you a probability bound which is comparable to what Chebyshev had given you, but there is a big hole in there, right. So, Chebyshev had given this to you for x greater than 3n by 4, or to put it in terms of the expectation, x minus n by 2, where n by 2 is the expectation. So, the random variable x taking value away from its expectation greater than or equal to n by 4, this is a very large quantity, right. It required n by 4 to give you a probability of 4 by n. Now, look at what Chernoff is doing. To give you a probability of 2 by n which is comparable to 4 by n, the range it is allowing you to play with is very small, it is square root n almost, there is a log n correction term, which was earlier linear, now has become sublinear, right. Square root n, you have come down by that much. Earlier, Chebyshev to give you 4 by n was allowing you a range of n by 4, but Chernoff is giving you that almost comparable value where the range is very small. Mind you, I am playing with the same random experiment, my setting is just the same, n independent coin tosses of an unbiased coin, same setting, but see what the story that Chernoff is telling you and what Chebyshev is telling you, right. This quantity, this is sublinear in n, right. So, log n, square root n, these are functions which are much below n, they grow. So, n grows much faster than square root n, right. So, Chebyshev is giving, Chernoff is giving you a almost comparable probability bound by making x stay very close to its expectation, right? X minus n by 2, that is the expectation. So, you are saying that the random variable taking value away from expectation by that much. Now, that much, the square root term is much below n by 4. It is a function much less than n by 4. So, Chernoff is actually giving you a sharper bound. If you had allowed it the range of Chebyshev, it would give you an inverse exponential, but if you want the same probability out of Chernoff, then it can squeeze the range. Now, this is telling you that the random variable is really concentrated around its expectation. As I said, I want to say that a random variable x follows a nice distribution. By that I mean that with high probability it stays close to its expectation. By how much? That is that quantity. What is that probability? This is the probability. Mind you, I started by saying that you can play around with the values and the probabilities. I showed to you one such game, and you can kind of play around with these values to get newer kind of bounds. So, I would stop here. If you have questions, I will take it.